We started by copying this diagram down, so that's a good place to start. Oh, and then OneNote froze on me. It's a good start to any video. Okay, so I would suggest now that you've got that diagram copied down that you just make notes on that diagram. You don't need to copy all this down, and I probably won't give you enough time to copy all this down. It is on the OneNote though, if you do want to copy it down later. Oh, this is frozen, sorry. Yeah, you don't need to copy this down. So I'm just going to go through some things quickly just to remind you of things that you'll need to know. And again, I've stolen a few things from different textbooks just to help me out with these diagrams. Firstly, the normal distribution requires some skills relating to measures of centre and measures of spread. Stuff you already know. So the measures of centre, you'll need to know how to find the mean. And the mean is just add them all up and divide by the number of scores. And you probably won't need to be able to find the median. And in a lot of cases, you probably won't need to be able to find the mean either. You just need to understand what the mean is. It's probably going to be given to you, or you might need to find it in a different way, and I'll explain that later. In terms of measures of spread, you will need to understand the idea of a standard deviation. And so that's important as well. So just to remind you verbally of what a standard deviation is, when we're talking about standard deviations, we're trying to classify how spread a set of data is. So to determine the standard deviation, we calculate the mean, and then we look at the average distance each data point is from the mean. And that seems like a pretty simple calculation, whereas the standard deviation formula is quite complex. But the standard deviation formula, you'll see, involves getting the distances, x1 minus x, x2 minus x, squaring those distances so that it makes all the values in there positive. Otherwise, if you average the distances, you actually just get 0 because that's the definition of the mean. So we square them all to make them all positive, and then we average the squares, and then we take the square root to undo the squaring. It doesn't quite undo the squaring because we've done a sum in the middle, but in essence it does. So when you do the standard deviation, you might have a set of data with a standard deviation of 4. The 4 doesn't mean a great deal, but it does give you a bit of a sense of magnitude. So if your data was all in the thousands and you had a standard deviation of 4, that's quite compressed. But if your data was just the error in the lengths of nails to the nearest millimetre, and they're in the thousands, although 1,000 millimetre nail seems quite long, then 4 might be quite a lot. Well, I would expect that if you're producing something or mass producing something, you've got very, very little error. If 4 was your standard deviation and all your numbers are single digit, that's quite a widespread. The good thing about standard deviation is when you're comparing two sets of data. So if we had, say, this Math B class maths results, and your standard deviation was 20%, and the other Math B class had a standard deviation of 5, well, then we could make the conclusion that they're significantly more consistent. Obviously, the mean's really important. If our mean was higher, that would then indicate other stuff. But the standard deviation is a really good comparative tool as well. You won't need to calculate standard deviation. You'll be given the standard deviation, or you'll need to find it from normal distribution information. And I'll get to that as well. You'll also need to have a bit of just remind yourself about data stuff. There is 2 types of data, categorical and numerical. We're not really dealing with categorical data, but it's there. So if I collect data on your eye colours or whatever, favourite sport, that's categorical. Numerical is when we're collecting numerical data. And then you had discrete and continuous. And discrete is that countable data. That is where we use the binomial probability. Continuous is measurable data, and binomial probability doesn't work because measurable data can be a whole bunch of different numbers. So that's where we're heading. I'm going to move down now. Like I said, I might not give you enough time, but that's on the OneNote. This is a big picture. You've copied one of these diagrams already. This is the normal distribution. So I'm looking at this diagram here in the top left-hand corner. Now, what this diagram tells us, and I've written a couple of things here. Or where have I written? So technically X exists everywhere over here on the right hand side. So what I'm saying is that this bar doesn't quite touch the x-axis. It carries on forever. That is the theoretical approach. Within context that might change, but theoretically X goes on forever. But what we know is if the mean is in the middle here, that's the most likely thing to occur. So for example, if I took, say, the height of students in year 12, the mean might be 170 centimetres. The most likely thing to occur if I pick somebody at random is that they're 170 centimetres, or maybe a little bit shorter, or maybe a little bit taller. It's unlikely that they're up here at 190 centimetres. But maybe there is one person who's 190 centimetres. It's just there's not many people here. It's unlikely to be 150 centimetres, but maybe there is one person that's 150 centimetres, and they're down here. Most people will be in here. So this shape actually represents, it's a probability distribution. And we did some earlier this term. This is another format of it. And when we have continuous data randomly selected, we would expect there'll be a lot of data in and around the mean, less data on the edges. And that's what this looks like. Within big sets of data, where there is no other factors, we can assume a normal distribution. So if we take, for example, the height of, and we've got to be a bit careful here with heights of people, because heights of people can be a little bit bimodal, and I'll explain that in a second, but let's say we take the heights of 18-year-olds across Australia, we could make the assumption that that's normally distributed. The only issue is that there can be a slight gender bias, so it might be bimodal. There might be a slightly taller average for boys than there is for girls, and you might end up with a sort of double peak. So you've got to be a little bit careful of that. But if you take out those situations, then you can assume this normal distribution. The QCS is another good example. So they use this for QCS scaling, etc., all the time. They use standard deviation and mean. What happens in the QCS is they have an average grade, and most people get about the average grade. And there's some people get a really amazing grade, and some people don't do well at all, but there's not many of those people. And there's more people in the middle. And it follows this trend every year, because there's 28,000 Year 12 students, and so you're not going to get any weird skews. So there's that. Within context, and I've said that X does go on forever, and forever in this direction. Within context, obviously this is limited. So that QCS context, obviously no one's getting below 0 marks. And in all likeliness, no one's getting 0 marks. So, you know, if you do the multiple choice, it's 100 questions. You're probably going to get 20, 25 of those just by guessing. So no one's getting 0 marks. There's going to be a lowest mark. There's going to be a highest mark. So within context, there is a bit of a cutoff, but theoretically, the probability distribution function that represents a bell curve goes on forever. And here's a little bit of detail. So it's called a bell curve. It's symmetrical, and that's a really important feature that we'll use. And the area below that curve is 1. Now, we have changed the order of things for you guys because we're doing that assignment in term 4. We're going to do definite integration after this topic in a couple of weeks. And definite integration is where we use integration to find area under a curve. So there's a function, and you'll see it if you have a look in your textbook. We don't require you to know it for the exam, but there is a function that represents this distribution. And if you calculate the area, the integral between negative infinity and infinity of that function to get the area underneath, it is exactly 1, because all probabilities add up to 1. So that makes sense. X can technically exist everywhere. And then we have this, and you wrote this in your diagram earlier. It turns out that in any set of data that can be approximated by a normal distribution, 68% of that data will exist between -1 and 1 standard deviation. So it'll be within 1 standard deviation of the mean. So if for example, we can assume that the Year 12 Math B results in the next exam is normally distributed, and that the average grade is 40, and the standard deviation is 8, 68% of you should get somewhere between 32 and 48. That's 1 standard deviation of the mean. That's if we get that skew. That distribution, that's what I'm looking for. So 68% of data lies within 1 standard deviation, 95% lies within 2 standard deviations, and 99.7% lies within 3 standard deviations. And that's how this works. So we use that information, we use mean and standard deviation, and this information here to calculate probabilities. And that's what I'm going to teach you over the next couple of weeks. One really common context, which I'll write on here, it's not on here, and you'll draw this shape a lot. So here's my, oops, that's just moved on me. There's my normal distribution. Now, there is a common context here where it's designed so that the mean is 100 and the standard deviation is 10. So it goes up to 110, 120, 130, down to 90. Does anybody know which context I'm talking about yet? Pretty old context. Most people don't believe it really works that well anymore, but it exists. So this is, sorry? IQ. So this is an IQ scale. IQ is designed to follow the normal distribution. If you have 1 million people sit an IQ test, they are saying it should follow this. And then they're normalising it. This is called normalising it. So your score on an IQ test might be 52. They will scale that so that you are in a position based on an average being 100, 110 being 1 standard deviation above, etc. So you will have heard, if somebody gets above 130 on an IQ test, they are a genius. And whether that's right or wrong, and whether you believe an IQ test or not, what we do know mathematically is if this is a normal distribution, how many people do you think exist in here? What's the probability of being in here? Above 130. Any takers? 0.3. Sorry? 0.3 is close. 0.3% is close, but not quite right. But you're most of the way there. Less than 0.3 is right, but we can be precise. Remember, it's continuous, so we don't just cut a little bit out because of the 130. Any takers? 0.3 is 80% of the way there to the solution.
Something to do with it being infinite?
No, not quite. So I'll tell you what 0.3 is. 0.3 is above 130, but it's also below 70 because it's within 3 standard deviations, 99.7. So that's 0.3. So this is 0.15%. So 0.15%, that's 15 people in 1,000. No, it's not. 1.5 people in 1,000, my apologies. So one person every 666 will have an IQ of above 130, if the scale works. And I'm not here to debate whether the scale works, but that's the way that's set up. So as you can see, it is a really unlikely thing to occur that you're above here. That's extremely unlikely. And also we have down there. Now remember, it's a continuous scale. So what's the probability of being, now this is a discrete scale, but what's the probability of being exactly 3 standard deviations above the mean on a continuous scale? So if I say to you that the average height of 18-year-olds is 170 centimetres, the standard deviation is 5 centimetres, what's the probability that somebody's 185 centimetres tall? Any takers? And this is a bit of a trick question. I'll tell you the answer. The probability that someone is exactly 185 centimetres tall is infinitely small, basically 0, because it's a continuous scale. So if you actually came up to me and said, hold on a second, I'm 185 centimetres tall, actually you're probably somewhere between 184.5 and 185.5, and you've rounded it. No one's exactly 185 centimetres tall. So with a continuous scale, you can't actually work out the probability of an exact point. You can only work out the probability between 2 points, or of a tail. An exact point doesn't really exist. Okay, but we usually take continuous data and round it to some level, so you'll see that as well. So that's the standard deviation. That's the diagram I suggested you drew earlier. I'm hoping you did. They're the concepts behind it. I'm going to take you through standardising scores, so standardised scores against raw scores, and then give you a worksheet on this. And then later this lesson, I'm going to take you through finding some basic probabilities. Okay? So we have 2 things that we'll talk about. We're going to talk about X scores and Z scores. They'll both come up a lot. The X score is the raw score. It's the raw data. It's me saying that the mean is 170, the standard deviation is 5, and what's the probability that you're 175 centimetres or more. 175 is an X score. It's raw data. It's from the context. On the other hand, we have a standardised score. A standardised score is what we're just using in the diagrams above. That diagram you drew down, you did 0 standard deviations, which was the mean. You did 1 standard deviation above the mean, 2 standard deviations above the mean, and 3 standard deviations above the mean. You took the raw score and you talked about it in a standardised way. How many standard deviations above the mean or below the mean are you? So a standardised score is called a Z score, and this describes how many standard deviations from the mean you are. And I've written that down as how many sigmas from the mu. You'll have to get used to that notation. Sigma is standard deviation, mu is mean. let me make that little note here in case you haven't written that down. This is equal to SD, and this is equal to X bar, or the mean. And of course the standardised score is called a Z score. And I've got an example here, but I'll give you a bit of time to write that down before I run through the example. So I've talked about the raw score and the standardised score, and here's an example. A set of raw data has a mu of 28 and a sigma of 3. So these are raw scores. I know my mu and my sigma. So if I drew this now, hopefully you can see, and I've just zoomed out a little bit there, and I've got two diagrams here. No, I don't. I might draw, I'll draw it on this diagram, X value and Z value on there. If I drew this now, I would have on here in purple, my mu is in the centre, so this is mu, and in this case it's 28. And then one standard deviation below mu, so this is mu minus sigma, this is 25 because standard deviation is 3. And two standard deviations below mu is down here, so it's mu minus 2 sigma, and this is 22. And three standard deviations is mu minus 3 sigma, sorry, and that's 19. And hopefully you can see where I'm going with this. I'll just finish it off, and we'll add the Z scores on a little bit later. So I've got mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. And that's 31, 34, and 37. Now, logically, this question asks me to determine the standardised score at x equals 28. So remember, the standardised score is the Z score such that the number represents how many standard deviations above or below the mean you are. So how many standard deviations is 28 above or below the mean? Any takers?
None, because the mean is 28.
The mean is 28. So it means that this one here, 28, has a Z score of 0. It's no standard deviations above or below the mean. It is the mean. What about 31? How many standard deviations above and below the mean is 31? Maybe somebody just said it, I didn't hear them.
2? No.
1, good, because the standard deviation is 3. 28 plus 3 is 31. So the Z score here is 1, because it's 1 standard deviation above the mean. 25, what about that one? Say it again, sorry? Negative 1. I'll take negative 1, good, because it's 1 standard deviation below the mean. So it's negative 1. 26.5, this is where it gets a bit tricky, but you can work this one out. What's 26.5? Any takers? Yeah?
Is it half?
It is half, and something with it?
Or negative half?
Negative half, because it's below. Okay? Now, let's go through that process that Sky's just gone through there. I'm going to assume a process you just followed, okay? And that is 26.5. I want to work out how many standard deviations above or below the mean that is. The first thing I need to work out is how far above or below the mean it is. So I've got that 26.5, or hopefully that's what you did. 26.5 minus the mean, and that gives me negative 1.5. And then I need to work out, well, negative 1.5, how many standard deviations is that? So I get the negative 1.5, and I divide by 3. And this is kind of like the idea you did in primary school. You know, I've got 10 lollies. How many ways can I divide that amongst 5 people? I divide it by 5. Here, how many 3's in negative 1.5? I divide it by 3. And it gives me 0.5. That thinking creates this function. So I know people are copying this down, but I'm going to scoot across to the side. This is your how to calculate a Z score from a raw score. So you get your raw score, you subtract the mean, and you divide by sigma. And of course, we could use X bar, and X bar seems to pop up a bit in this reference, or we could use mu, which is the mean as well. So X bar, mu, doesn't really matter. But I think X bar appears in your textbook, which is why I did that. And I can rearrange this. This will be important as well. What if I know the Z score, but I want the raw score? Well, that's easy to rearrange. I get Z sigma equals X minus X bar, which is just mu. And then I get x is equal to z times sigma plus x bar. And that would give me the raw score if I knew the z score. So that really helps as well. Anyway, that's, I'm going to zoom out a little bit so you can see both, and I'm sorry if it's getting too small, but that's the width I'm dealing with. But I want to do this last one here, because z equals 0 was easy, z equals 1 was easy, z equals -1 was easy. They're very logical. Whole numbers of standard deviations, great. Z equals -0.5 was doable without the formula and with a logical approach, but it's starting to get a bit harder now. Z equals 21.7 is a bit harder again. So to calculate this one, I'm going to just change it back to purple. To calculate this one, I've got Z is equal to 21.7 minus 28 over 3, which is equal to 6.3 over 3, or negative 6.3, and that's equal to negative 2.1. So Z equals negative 2.1. That tells me 21.7 is 2.1 standard deviations below the mean. And I can't stress enough that this is one of those topics, like you're probably looking at some of this now going, I don't know what's going on, and I fully understand that, it's abstract. But the actual calculations I'm doing, they're pretty simple. And you've got to get yourself beyond the, I don't know what's going on, practice it, ask relevant questions, and you will find it comes together quite quickly. But you do have to get past that, I don't know what's going on. Part 6 there says, show each of the x values and z values on a normal distribution graph below. So I'm going to scoot down and finish that off. We've already done the raw scores. Now I'll do the z scores in green. So the z scores are, the z score at the mean is 0. So there's 0 standard deviations above and below. The z score at 31 is 1, because that's 1 standard deviation above, and we calculated that in part B. The z score at 25 is -1. The z score at 34 is 2, that's 2 standard deviations above. 3 standard deviations above. This is -2, this is -3. Hopefully you can see that that z score represents that number there, the coefficient, the number of standard deviations we've taken away. The z score is -2, -2, -1, -1, 1, 1, 2, 2, 3, 3. The z score is just a measure of how many standard deviations above or below you are. But what it does is it standardises it. It's a really good comparative tool, because if this class has an average in the exam and a standard deviation, and you want to know where you sit compared to your friend in the other class, but they've got a different average and a different standard deviation, or you want to compare yourself to somebody in Maths A, okay, and this class got on average 40, and the standard deviation was 8, and you got 52, well, you can say I'm 1.5 standard deviations above the mean. And if your friend in Maths A, the average is 65, and the standard deviation is 5, and they got 70, it looks a bit like they did better. They got a higher score, but they're actually only 1 standard deviation above the mean. So that means that you've done better than them. That's a comparative tool as well. So once you standardise the scores, you can do a direct comparison. When they're raw scores, you can't make that comparison because the mean standard deviations are different. So here's my question, which is like that. Example 2, which score is better? 28 out of 40 in an exam where the mean is 24 and standard deviation is 2, or 37 out of 50 in an exam where the mean is 30 and the standard deviation is 5. And then I've got a z-score question below that. So I want to know which of those scores is better. And we're going to work through that now. Anybody want to have a guess which one's better? Straight up?
The second one.
Second one. Top one. Top one. Second one? Okay, let's do the calculation. So the first one has a z-score equal to 28 minus 24 over 2, which is equal to 2. The second one has a z-score equal to 37 minus 30 over 5, which is 1.4. In terms of looking on the normal distribution graph, student 1 exists about here at 2, whereas student 2 exists about here at 1.4. They've both done well. They're both well above the mean. but student 1 has done better, just based on averages and standard deviations and stuff, okay? So that's what this comparison is. And it's a useful comparison to use when you're looking at your scores, and that whole process you go through with Mr. Vanderbosch when he says you never know what's going to count, because you never know what the QCS mean and standard deviation will be for each of these classes. And if the mean and standard deviation puts you really high and means that you get scaled up a lot, you're in a great place. And it might be a subject that you think is going to be your worst is not actually your worst because this happens. A standardised score is better than you thought. So you've got to be careful with that. Question B. If I got a Z-score of negative 1.5 in each, what would my actual mark be? So remember that for that Z-score, we have X, the raw score, is equal to Z sigma plus the mean. And that makes sense because Z sigma will tell you what raw score you were above or below, and then you add the mean on to get that position above or below. So negative 1.5 is my Z-score, and so for person number 1, I get X is equal to negative 1.5 times 2 plus 24, which is equal to 21. And for the second person, I get X is equal to negative 1.5 times 5 plus 30, which is equal to 22.5. So you can take a Z-score back to a raw score. And this is pretty common as well. You might find something where, for example, to get into a competition, it could be sporting, or it could be, let's say, golf, and they want to get certain people, pick people in golf. They want to pick the top 5 people out of 100 players. Now, you know from our work earlier, well, let's know that 5 people is not going to work. Yeah, okay. 5 people is not going to work because we've got top and tail, but we know that 95% of the data exists between 2 standard deviations. So 2.5% of the data is above the top 2 standard deviations above the mean. Now golf works oppositely. Golf, you want a smaller score. So we want to take the people away that are the best 5, and we might do that by creating a cutoff. So instead of worrying about just taking the best 5, we might create a cutoff so anybody can get through. And say the cutoff is based on the scores and the standardising component. To make it fair, we're going to take a cutoff of anybody that is below 1.8 standard deviations below the mean, and they'll be our best. And it should be about 5 because that's how the normal distribution works. And so you will say, well, I want my Z-score to negative 1.8, and I know my mean and my standard deviation. I can work out the cutoff and then use that cutoff to take or to accept or remove people from that group. Are there any questions? Okay, I do want to stop soon, and I think I'm stopping quite soon. Yeah, I'm just going to run through this example, which takes you a little bit further and should give you the access to most of the next exercise. I think, or let me just have a look. I wouldn't mind giving you a break. Yeah, I might just give you some time on this and give you a break, and then I'll come back and do some more. So I'll stop this video here.